Hello everyone and welcome to this course on control analysis and design using Python for grid connected systems. So with this very first lecture, I would like to welcome you to this course, and number two, since this is the very first lecture, I want to talk about what this course is all about. So number one, this is a very broad topic, that is control in power electronics. And this is the reason why it's very important that when you have such a course, it is important we define the scope of this course. What will be this course all about? So this lecture is actually into two parts. I will talk about one, what is the course not about? So what will this course not cover? And I will describe what this course will cover. The reason is because I do not want students to come with the wrong perception and then not find the course relevant for them. So before I even get started, I would like to talk about what we will not talk about in this course. So let's keep going. So to begin with, this course is not a masterclass on power electronics, right? I do not believe in creating A to Z masterclasses. I do not like courses which cover every aspect of a particular topic, but not going into depth, right? I like courses with depth. I go deep into a particular subject. That is what I like to do. So this is not a masterclass on power electronics, right? We will not be going through every converter that has been used over the past 40 years. That's not something you will see in this course. We will not be comparing different topologies or talking about when and how a particular converter was used and who started it and who used it and who adopted it. We are not going to be talking about any of these things, right? We are talking about grid connected systems. So it's basically grid connected converters. But even in this context, we are not going to be going through the applications of grid connected systems. So what that means is we will not be talking about what this grid connected system does. For example, we will not talk about how a solar panel or a wind turbine is interconnected to the grid, okay? Because this is the application. What we are interested in is the interconnection only. That is it. The application is totally a different topic. We are talking only about the control, design and analysis of converters connected to the grid. That is it. So this is a very, very specific topic that I'm going to be talking about. Applications such as solar panel integration, wind turbine integration, maximum point tracking, these are not going to be covered in this course. We are not going to be covering also other aspects of emerging technologies like how to charge electric vehicles or how fast chargers are designed or how you would charge a vehicle on the go. None of these topics will be covered, right? None of these topics are going to be covered in this course. So this is an online course, and it's important to note that this is an online course. We will not be dealing with hardware implementation. You will not be learning anything about hardware in this course because honestly, I do not see how it is possible to teach hardware through online courses. You do need a laboratory, and most often you do need the instructor actually coming and helping you physically. At least that's how I see it. Unless, of course, things change in the future. We don't really know. But as of now, none of my online courses will deal with actual hardware. There will be no circuits. There will be no hardware. There will be no oscilloscopes. There will be none of these. This is a simulation and programming course. That is it, right? Also, most importantly, all the programming and simulations I do will be in Python, but there is going to be nothing to do with the implementation on a particular platform. For example, I will not talk about how these codes can be converted directly for a DSP or for an FPGA, right? So there is going to be no talk about how you can convert all these codes to VHDL so that you can burn it on an FPGA and all those kind of things. That's not going to be focus of this course. There is going to be nothing about implementation. It is merely the concept of how we design a controller for a grid connected converter. Moreover, this course will not cover advanced power converter topologies like multi-level inverters, cascaded inverters and several others, right? We will consider a simple 2-level H-bridge converter as our converter topology, right? Because the main objective, as I said before, is the control design and analysis using Python. That is the main objective. The objective is not to look into advanced power converter topologies or talk about space vector modulation or advanced sine triangle modulation strategies. That is not going to be covered in this course. Now, the focus of this course, as I said, is to learn how to design and analyze control systems in the power electronics domain. That is what this course is about, right? So now I'd like to talk about in depth what I'm going to be doing in this course. So to begin with, this course will start from a circuit such as that of a grid connected converter and will describe how to take such a circuit and represent it as a control system problem. How do we take a simple circuit that we all know as power electronics engineers? If I were to take a grid connected converter, how would I draw this circuit? How would I write the equations? And how would I interpret it as a control system problem? We know how it is when you talk about it in electrical engineering, but how do you translate it to a control system problem? That is how we will begin. We will bridge this gap between power electronics and control systems by defining every control terminology in the domain of power electronics. So I'll be taking this example of a grid connected converter and I'll be talking about every aspect of the control system in this particular application. So I'll be talking about control systems with respect to power electronics, not with respect to inverted pendulums, not with respect to any of the other simple systems that most control systems courses usually deal with. This course deals only with power electronics converters. That's it, right? Of course, I'll be using examples, a few examples just to make the learning process easier. Some examples which are general, like how using control systems for driving a car, things like that. But that's mainly for the purpose of understanding, and there's not going to be any real control system analysis or design in those domains. All control system and analysis is done in the power electronics domain. So the most important thing is that as students, you will learn how to represent physical systems in control block diagrams from deterministic equations. In our case, since we are electrical engineers, since it's a power electronics topic, we are going to start with Kirchhoff's voltage law as our base equation. Of course, you can have Kirchhoff's voltage law, you can have Kirchhoff's current law, you can have many other laws and combine them together. And these are the equations that describe your power electronic converter. And with using this, I'm going to talk about how we can take these equations that describe the physical system and then convert it to control block diagrams. And this is always the first step in control, which is system representation. And this is what we'll start off with in this course. Now, going further, this course will use Python for everything. Alright, this course will use Python for everything because Python is free and open source. It is being aggressively developed and it is also being used for a wide variety of applications in scientific computing, such as artificial intelligence, machine learning, data science, computer vision, many others, right? That is one of the reasons why I would like to start using Python more for core engineering. So this course will show how we can use Python to do all our control system design and analysis. We will use Python for creating transfer functions for all our system representation. So for the system, which in our case is the grid connected converter, all the transfer functions will be synthesized using Python. We will use Python to then analyze these transfer functions to examine the performance of the system in different aspects. So we will look at the stability of the system, we will look at the performance of the system, we will look at the frequency response of the system, and many other aspects, right? We will then introduce basics of control systems and we will describe their significance in the context of a grid connected converter. So we will talk about how phase margin and gain margin can be used to analyze the stability of the system. We will talk about how we can analyze the stability of the system from the closed loop poles of the control system and how we can interpret the stability of the grid connected converter as a system with respect to the closed loop poles of the transfer function. So using Python, we are going to analyze this grid connected inverter as a control system problem. That's what we're going to do. We are going to represent it as a control system problem. We are going to then analyze it with respect to control system tools, and then we are going to deal with every aspect of this grid connected converter, which is a power electronics problem, and treat it as a control system problem. That's what we're going to do in this course. So we will use simulations to verify all our control designs. All simulations will be done using the free and open source circuit simulator, Python Power Electronics, to verify all our conclusions, right? Now, again, the only reason why I'm using Python Power Electronics is because I'm trying to promote Python, and this is free and open source. However, you can try and use other circuit simulators as well. The code is what is written in Python can be written in any other programming language and can be used in almost any software, so any simulation platform. So these simulations will be used to verify several aspects. So for example, using simulations, we will verify when systems become unstable. Because we've already used control system tools to analyze the stability of our system, our stability of our grid connected converter. And using simulations, we will then verify whether those analysis of unstable systems that we arrived at from control systems show up in simulations as well. So these simulations will also be used to predict how the system behaves in steady state. So for example, using control systems, we will define how we will try to predict how the system will behave under normal conditions for our grid frequency. And we will then verify using simulations that this is indeed the case. So therefore, not only can you predict that the system is stable or unstable, you can also predict exactly how much error you will end up with. And we will verify that this error that we get in simulations can be predicted to a fairly good extent through control analysis. So this way we will show how control analysis can be used to predict the behavior of our system, which is the grid connected converter. So therefore, this will make it possible to use mathematical tools to design each and every aspect of our controller for this particular application. So what are we going to consider as our system? We will consider a single phase H-bridge converter, right? Single phase H-bridge with a DC bus connected to a single phase 240 volt 50 Hz grid through a simple inductor filter. This is going to be our system. Very simple system. There are more advanced filters, there are advanced topologies, and depending on where you live, the grid can also change. If you are in North America, you can replace these values with 120 volt 60 Hz, right? That will be perfectly okay. At the same time, there are applications with more advanced filters. There are inductor capacitor filters, LCL filters, LLC filters, many others. We won't be talking about those. We'll start with the most basic inductor filter because the aim of this course is to introduce control concepts and not to start dealing with advanced power electronic concepts. So the focus of this course is to help power engineers understand control systems in the domain of power electronics. This is one of the reasons why I created this course, because all courses on control systems deal with topics that have nothing to do with power electronics. They will deal with simple systems, which are first order systems, zero order systems, second order systems, and many others. But they do not deal with actual power electronic converters, which most of us power engineers have to deal with on a daily basis. So this is the reason why I created this course, so that power engineers can learn control systems with respect to the converters that we deal with on a daily basis. That is the reason for this course. So this course is not to consider different topologies or any of those things. The focus of this course is control systems. So we have chosen a simple H-bridge converter and with a very simple inductor filter. That's it, right? Because the focus is how do we design the control for such a system, to introduce the mathematical concepts and the programmatic concepts that can be used for all these purposes. So this course, as I already said, is an in-depth course. This course is very, very deep. There's almost more than 30 hours of video content. You will find analysis and design of controllers for power electronics, and this course is divided into theory and simulations and programming. And there is this huge amount of simulation and programming in this course, besides theory. Theory is essential because for a topic like control systems, it is important that we first start with the theoretical concepts and gradually move on to start programming. But the main thing is almost every concept that you learn in control systems will be backed up with design examples using Python and simulations to verify our concepts. So this course will not be purely theory, is theory mixed with simulations and programming. So this is what the course is all about. I hope with this you have a fairly good, clear idea of this course. If you still have any doubts about what this course is about or whether this course is applicable to you, please do write in the Q&A forum and I'll be happy to help you. But going further, get ready for in-depth of control system introduction and also programming and simulations. So this course is going to be a hands-on course. I do require you to be programming continuously and also to be a theory course where you might once in a while want to pause the video and even solve equations on your own. So again, if you need any help or if you have any doubts, please do reach out to me in the Q&A forum and I'll be happy to help you. Otherwise, I will see you in the next lecture. Thank you so much and see you soon. Goodbye for now.